and whatever Harishchandra was doing. So what's happening? So as I was pointing out, my initial idea was to talk about unitary dual of UN. As I pointed out in my first lecture, compact Lie groups, actually every compact Lie group is going to be a subgroup of UN. UN is actually a very important group, not only in its own right, and its applications in many fields, not only mathematics, physics, and so on. And as I said, the construction of the unitary dual and the computation of unitary dual done mainly by Hermann Weyl has some sort of gives me a room to discuss a little about what Harishchandra has done. So I modified the title and I wrote on the legacy of Harishchandra, and for which I should be apologetic in the sense that I don't know much of, I haven't read papers of Harishchandra, though I know here and there something what he has done. But the main motivation is to see that our younger generation get interested towards the work of Harishchandra, and if not the work, at least a man like Harishchandra, and you appreciate, you listen with awe. So that was the idea. So unitary group, like we had SU2, it is a matrix group. It is also a linearly group, because of which exponential comes for free. We have exponential. We can exponential map. We can exploit that to map, and it is all n cross n unitary matrices. And we will be following the same strategy of what we have done in SU2. We look for suitable subgroups, and then we look for a naturally occurring representations. So in SU2, we have two compact abelian groups. So one is the diagonal matrices, the other being rotations. And of course, SU2 operates over Cn, which gives rise to representations consisting of homogeneous polynomials. And you have to prove somewhere how that they are all irreducible. Up to then, up to this, you are actually trying your luck. And then I have to apply Peter-Weyl theorem to say that these are the only representation, unless you have the beautiful celebrated Peter-Weyl theorem is applied, you cannot really parameterize unitary dual. So now, in order to apply Peter-Weyl theorem, I want you to recall what we have done in SU2. We first need an integration formula for the Haar measure for the SU2 group. And then we have one class of special function, namely class functions, or central functions, which actually is being generated or spanned by characters of irreducible representations. So therefore, I need the integration formula for class functions. And then, of course, I apply to realize hat G. Hat G is none other than the unitary dual of the group. So this is the strategy. We are going to follow the same strategy here and try to kind of grasp how much you can do. So here I have a subgroup, namely torus. This is called maximal torus. Maximal, I don't have to explain. It is torus. You see that you have these are the elements. It's of modulus 1. It's an abelian group. And the Lie algebra, as I said the other day, I have given you some computations. You have the exponential map, and you differentiate and take the value when t equal to 0. You would be getting the Lie algebra elements. It is of the form alpha i's are in real. They are all I of alpha 1. So, okay. So now you have an expansion. This is a group formalism. I may not be using much. And the important thing is the maximal theory are all conjugated. See, for instance, again, you go back to SU2, I had a group K, I had a group A, and both are conjugated. It is mainly because every matrix, a commuting class of matrices, can be unitarily diagonalizable. That is, diagonalizable within unitary group. So therefore, that is the same as saying that these two, any maximal theory is conjugated. So now, so this is the formal definition of a torus. So I will be going back and forth. On one side U to UN, on the other side compact connected Lie group. So for compact connected Lie group, I will be only hand waving, but whereas for UN, we shall do some computations. So you have, it is a torus, and this is the real result that every compact connected Lie group contains a maximal torus. If you don't have a torus, then identity itself is a torus, but you always have a maximal torus. I need to use the machinery of Lie algebras in order to say this. And see, the moment if you go for a compact connected Lie group, an abstract group, you have to look for a torus by means of the tools applied. And what are the tools available for us? We have a beautiful Lie algebra, exponential map, and try to understand the Lie algebra. But the understanding of Lie algebra is better, more powerful when the Lie algebra is over complex plane. You complexify it, and then you study them. And you come back to group, like we have done in the SU2 business and SO3 business. Okay, so now you have a definition called normalizer. This is a easy definition in algebra. And the important thing here is it is also closed-up group. It is the mapping here is continuous, so therefore it's closed-up group. The connected component is actually turns out to be T. And the important thing is it is discrete. This group is discrete. It is this group is discrete. A discrete thing sitting inside the compact group will be finite. It's called Weil group. We denote it by W. So therefore, whenever I have a torus, I have a corresponding Weil group. This is what we call, and every torus T has a generator. Indeed, generators are dense in T. It's an application of Kronek's theorem. Does it ring you any bell in your mind? Some 3, 4, 5, 6 weeks ago, Professor Malavika was talking about Kronek's theorem, and she was giving a cute proof as an application of Plancherel theorem she was discussing. So what is Kronek's theorem? This is the Kronek's theorem. If you have so many elements, look at this has a generator if and only if this is linearly independent over Q. I will not prove this because it is already proved. So whenever I have such a situation, then it will produce me a generator in T. So this is, so therefore the theorem is an application of Kronek's theorem. Okay, so now let's come for the integration formula. We have now we discussed about torus. So this one, you know that Haar measures on a compact group is finite. I normalize. Similarly, this one is also, I have a harmonic. And then there is a result. This you have to believe me. So this integral is given. So you see that I first integrate over T, and this one is becoming a function on G by T. And add representation, I already explained. You take any element of the group and any, okay, you take an invertible matrix that defines an odd representation on any matrix by X going to GX G inverse. GX G inverse. So it's almost like inner automorphism. But again, as I said, when you go for abstract theory, adjoint representation has to be properly done. So here, fortunately, we are looking at matrix groups. I have this one. This actually, if I have time, I would love to compute because it is actually the Jacobian. So when you have a change of variable formula, you have a Jacobian, calculate the Jacobian, and see, for example, a postgraduate student can calculate this. And when I take f to be a class function, so this one will come out because it doesn't depend on g. Sorry, the integral comes out, and I have add t inverse minus I dt. This is for the general compact connected Lie group. I have this integral formula. This is again done by Weil. Okay, so now I take what happens to UN, unitary group. In unitary group, this is the torus. And for the torus, there will be a Weil group. I forgot to mention one. If this is conjugated in T, then there will be an element from the normalizer with the same conjugation. So what I mean to say is the conjugacy class belonging to is the same as conjugacy class, which I take only with the elements of normalizer of T. That is one of the reason why that Weil group comes here. Okay, so now I take, this is our well-known symmetry group. So things are a little easy. Why is it easy? Because I take the generator. If I have a generator of T, then I define, if I take a sigma, I define a map. So what is the map? First, I define it over this fixed generator. It is the natural map. Sigma gives rise to a new element, but you see that because it generates. So, and this mapping is a homomorphism, I can extend to all of T, continuous. So therefore, it is the definition pi sigma acts over T. But you see that this pi sigma T naught is again an element in the T, and it is conjugate. Sorry, it is an element in G, so it has to be conjugated. So I have a conjugation, and because of the definition, this will be in NT, normalizer of T. So I repeat, I begin with a element in Sn. I get an element G sigma in normalizer of the T. How do I get it? I employ the sigma on the generator. Now, if you take any element, you see that the eigenvalues of T naught and this one will be same. So therefore, there will be a sigma. Like, see, the eigenvalues here are both are same. So therefore, I always have a sigma satisfying this. The moment if I have this one, that gives rise to an element in Sn. So therefore, for every element in NT by T, I have a sigma, and for every sigma, previously we have seen that there is a element. So therefore, NT by T is actually the Weil group. Weil group is actually going to be Sn. So life is easy little. So now this is needed for the integral formula. So I just it's an I look at all the generators and it forms a dense open subset. So fortunately, we are living in a regular measure. So therefore, if something happens on an open dense subset, then I don't have to bother much about it. So most of the time, we will be working on omega. Okay. So this is important. See, now what happens is this G is set of all skew Hermitian matrices. Because capital G is UN, the corresponding Lie algebra is given by skew Hermitian matrices. And this fellow is actually the diagonal matrices with imaginary part, purely imaginary part. So what is left is this one, the set of skew Hermitian matrices for which the diagonal entries are 0. So therefore, the Lie algebra of G is actually the direct sum of the P plus circle, P direct sum torus as an algebra. And this one, you see that now I don't have to calculate. See, if I take an element in T, it commutes. So add becomes trivial. So I have to only look at here on P. See, do you remember add is a mapping on the Lie algebra. For every T fixed, add is a mapping on the Lie algebra. Now add and T will not give you anything, abelian. So therefore, I have to only calculate over P. P is this one. So this one is an elementary calculation again. Add T and Eij is the matrix whose ijth entry is 1. So this you can calculate easily. So this one is this. And so now add T inverse minus IP. So I not equal to this one. I pull out TI inverse. When I pull out TI inverse from this product, there will be T1 inverse, T2 inverse, and so on. That would give you the determinant, which is going to be absolute value is 1. So that goes off. So what remains is I less than J, Ti minus Tj square. This is not something new. This is one of the fantastic matrix which keeps coming at many places, namely Vandermonde matrix. So therefore, the integrand in the integrand function in the integral formula is given by a Vandermonde matrix. So now our second step is over, namely we are able to get the Wales integral formula for class functions, which is given for the group UN, is given by this n factorial is the number of elements of the Weyl group, Sn, and I have this one. This is a beautiful formula. So this is one important aspect of harmonic analysis. Many times you do abstract things, but finally the calculation is something to do with your hands, elementary calculations. So it is both elementary calculation oriented and very difficult abstract things like we have seen in the last lecture, simply connected and so on. That is one thing which makes harmonic analysis is more interesting. So I was able to calculate this formula, which I will be using it like in SU2 at the end of the calculation, at the end of the lecture. So now you see that I am complexifying it. I am complexifying the Lie algebra of the torus. So it is given like this. And now I'm going to the third step, namely, I'm looking for a naturally occurring representations. What I do is I will look at the characters. You already know what is a character. This is Ti. Ti is indeed is of the form e power I 2 pi some number. And I am putting a mu I over it. So that will give you a new character, isn't it? So this is a character. When one-dimensional torus, you see this, isn't it? Now I'm looking at n-dimensional torus. And there is a linear functional corresponding to it when I apply the exponential. This is, I take any element in the complex Lie algebra and I multiply, this is integers, mu i's are integers, I forgot to tell, and mu I is zi. It's called weight. Don't ask me why it's called weight, you will now know a little later. And it satisfies this property. You see that in a simple-minded way, I look at a character on T and I am getting some linear functional on the Lie algebra H. So this mu1, mu2, mu-n gives rise, this is an n-dimensional Lie algebra over complex plane. It's given by, I'm taking only integers and what I get is I get a character. When I have a character, I get a linear functional on H. So both are interconnected. There is a bijective map between the weights on UN and the characters on T. Characters are given by this one, and I call it as a weight, and I collect all the weights possible. Let's see what do I do with that. Whatever I have done there, I can repeat for a general representation. So I take a finite dimensional representation. Then I have a derived representation, which we have seen last time. D pi of x is given by d by dt t equal to 0 exponential of phi pi of exponential tx. That's the commutativity. And the important thing is this satisfies this because this is a unitary operator. Finite dimensional unitary representation. All compact groups representations can be unitarizable, and because of which I have this one is symmetric. So therefore, this is beautiful. See, X is a complex vector, and it splits beautifully because the adjoint goes to adjoint. Okay. So now, if phi is any irreducible, any finite representation, a linear function is called a weight associated to pi. I have given a general way of constructing weight. Now I am looking at a representation, I am calculating the weight. And I say that this is a weight if there is a non-zero vector satisfying this. D by T. So this tells me that mu h is alive, or otherwise it's zero, isn't it? T pi h, I get it through mu, which is alive. Okay. So now I want to say that the weight associated to this representation pi is indeed a weight which I have defined in the previous slide. So how do I do it? I do it using the formula here. Pi of x, you can see that it is actually. See, in the whole slide, I only see that the weights associated to the representation pi is actually a weight. I have defined a weight on a Lie algebra, generally, using any torus, any character. So now I am taking them, I am classifying them. When I have a representation pi, I have p pi. Similarly, I will have p rho. Similarly, I will have another representation. What do I do with that? Let us see. The important thing is not showing up. What? Huh? Yes, you put it on the top. So it says that you take any finite dimensional representation, then you look for the weights and you have a direct sum. So p pi h pi u. So any representation is a direct sum corresponding to this. There should be a name for that. I call h pi u. H pi u. Okay. It doesn't move. So now there is another algebra which is coming up. Fortunately for you and things are easy. By the way, what is GC? GC is G is the Lie algebra of UN, which is actually skew symmetric matrices. When I complexify, I get GLNC. Hermitian, so any complex matrix is a sum of skew symmetric and symmetric matrix. Hermitian and skew symmetric matrix. This is, in that, I look at all the upper triangular matrices. So that I call it as that's going to be a nilpotent Lie algebra, nilpotent subalgebra. I call it as N. And I make a passing remark that such an algebra you need to compute or you need to have it even for a general semi-simple Lie algebras. You have N. And for this one, things are easy. Okay. So now I say that now I am defining what is called a highest weight vector. Yeah, when I say that something is a weight vector, it satisfies this property. V is not zero, satisfying this. Is it okay? So I have. So now I want this to be zero for all n. That is, it is growing up on H and on n, it doesn't, it is becoming zero. That is one of the reasons why it's called the highest weight vector. This will be clearer in next 2-3 slides. So I say that something is a highest weight vector if that d pi applied to the nilpotent algebra kills that vector. And for this, it is a diagonal operator. You see that d by h restricted to h pi mu is a diagonal operator. So actually scalar operator. Correct? So therefore, this is going to hold the key for us to understand the unitary dual of UN. So now let's take a finite dimensional representation. Then please read the theorem carefully. It's a beautiful theorem. There always exists a highest weight vector for any finite dimensional representation. And I give a characterization of the irreducibility of this representation in terms of the highest weight vector. How do I give? I say that it's irreducible if and only if that h pi mu which I defined is actually one-dimensional. That is, so the moment if it is a weight vector, h pi mu will be non-zero, it will have v naught. Now what I want to say is it is the only basis, meaning that's going to be one-dimensional subspace. H pi mu is a one-dimensional subspace. Is it okay? Are you still with me? Following? So what happens is, so most of the time, what do I do is I begin with a finite dimensional representation, which I don't even know how does it look like, but I bring all the information on the Lie algebras. How do I get it? You consider one diagonal matrix like this, H1, H greater than with this condition. And then I look at, this is fixed. This is a fixed element in the what they call Cartan subalgebra, that is script H. And this is all real numbers. And it satisfies this condition. Now I go for P pi. P pi will have only finite number of elements because it's a finite dimensional representation. I cannot expect many. Sorry. And I look at among them, one will be the highest on H naught. What is lambda H naught? Lambda H naught is the value which is bigger than mu H naught. Is it okay? Mu H naught. So now, if nu belongs to H pi lambda, then nu can be seen to be a highest weight. This vector is going to be highest weight vector. So far, that distinction I forgot to mention. I was talking about highest weight vector. That is easy to see. You have to do, you know what is this? H naught x minus x h naught. If you calculate, you will see that this will be given like this. And secondly, d pi h naught of d pi x v is again using the Lie bracket business, one can write like this. But you know that lambda h naught is the maximum thing one expects. So therefore, this has to be 0 because hi minus hj is positive. So then it becomes 0. I forgot to write. So therefore, you see that if with h naught like this and a v, any element belonging to this for the lambda, it will give you a highest weight vector. And this proof is pretty straightforward. Assume that, for example, this is one-dimensional space. If I have a sub-representation, then you know that because of the unitarity, H perp is also not zero. So I got two sub-representations. So therefore, there will be two highest vectors which will be available. One belongs to K and the other belongs to K perp. Therefore, they are orthogonal. So that contradicts the assumption. So therefore, it is irreducible. Now, on the conversely, if you assume that H is irreducible, if nu naught is the highest vector, which you get it because of the first step, and if I have any other highest vector, you can see that it is, if I have it, this is 0 because V naught is orthogonal to W. This is a diagonal entry. And this one is the n star is all the adjoint of n. That is all lower triangular matrices. And this will be 0. So you already know because it is the highest vector, weight vector, on n it is 0, on n star it is 0, on h it is 0. So therefore W has to be 0. So this theorem is a beautiful theorem. So now I say that it is about the domination of, I call it this is not very important indeed. So I first defined what is called highest weight vector on a vector space. I have the eigenvalues or eigenvalues corresponding to it. I say that something is dominant if it satisfies this property. And this is, I denote it as P plus. Just now we have seen that the highest weight is a dominant weight. So if phi is an irreducible representation, I do have a highest weight vector, and therefore I have a dominant weight. So therefore there is a map. I have a mapping from G hat into P plus. Look at this little carefully. I take any abstract irreducible unitary representation of UN, I associate with some elements, some numbers in P plus. In P plus is consisting of all dominant weights. I have a weight and I say that it's dominant if it satisfies this property. And now I want to prove that this is the parameterization. Is it okay? So this is what I called step number 3, namely, you look for some possibly naturally available representations. Now I want to prove this one. There are two things I have to prove. One, I have to prove it's injective. That means if I have two representations which are equivalent, that gives rise to a same weight, dominant weight. And for every dominant weight, there is a corresponding representation. I recall what we have done in SU2. I have representations, and then I confined myself, I brought down to torus, and then there was some function coming sin and theta by sin theta, and then I used the character formula of Weil, and I used Fourier series to conclude that any other representation which is orthogonal to those representations has to be 0. It is almost same, but more complicated, of course. So here I cannot have one-dimensional thing. There are n-dimensional coming up. So this is what's happening. Now you see that the whole scenario is changed now. I am going to do some algebra. So I have a trigonometric polynomial. You know trigonometric polynomial over the torus. I say that it's symmetric for all sigma belonging to Sn. So there is some typo here. Skew symmetric if it satisfies this. And then how do I symmetrize a polynomial? There is something, yeah, right. So I take t power alpha, alpha is belonging to Sn. So this will be a symmetrized monomial. Similarly, I can symmetrize. This is not important. Actually, I wanted to take it out. I forgot. Okay. This is symmetric, and similarly, I have skew symmetric polynomials. They are not polynomials, they are trigonometric polynomials. I look for the basis of PS and PAS. I write in the language of algebra, I write it as a partition like this. So I define A alpha T to be E of sigma T alpha. Such a thing, you would have seen it in the differential forms when you have wedge product. So now this is the signature. For example, let's go back to our van der Waals matrix. This is given like this. Then this A alpha T epsilon sigma T power alpha, correct? And here Vt also can be thought of as A lambda T, A delta T. A delta T is a skew symmetric function, polynomial, which is actually your van der Waals determinant. I look for delta. Delta is given like this. This you have to calculate. I don't have much time to do that. So now this forms a basis. So all these elements of this form forms a basis. So this is a monomial, symmetrized monomial. But here I am taking it over epsilon sigma signum so that it becomes a skew symmetric. And it forms a basis. And if you multiply with van der Waals, that's an isomorphism. See, it's a ring, symmetric polynomial. So trigonometric polynomial forms a ring. If I multiply, I get a symmetric and anti-symmetric trigonometric polynomial functions. I have not said anything about the degree of the symmetric polynomial. I look at all symmetric polynomial possibly, but mostly, so I can have an infinite sum, but most of the elements would be zero. So now, this is a little technical. What I do is, if I take strictly positive, if I take a lambda delta with that, then it becomes like this. So this is not something new to you. This is your dominant weight. You have a dominant weight with lambda 1, lambda 2, lambda p. What is p? P here is the degree of a symmetric polynomial. And this is a partition of p. This is a partition of p. And I have as many polynomials as possible. This is where this is the crux of it. Like we had sine and theta by sine theta in SU2. For every alpha belong to P plus, you have a dominant weight. I define like this. And this is Q symmetric, this is Q symmetric, therefore it is symmetric. And also you may ask a question whether it will be a polynomial. You have to again believe me, they get cancelled, Ti minus Tj. So therefore, it is actually a symmetric polynomial. So what I was doing for the last 5 minutes is, I am looking at all the possible symmetric trigonometric polynomial. I define a Schur function. What do I do with this Schur function? Like in SU2, I associate a Schur function for a character. What is that? If phi is an irreducible representation of un, I go back to un. I consider general irreducible representation, and any irreducible representation will have a highest weight, as you know. That gives rise to a dominant weight. And if you have a corresponding parameter, then that will be given like this. So did I write? Lambda is the highest weight. Corresponding to lambda, isn't it? For every lambda belong to P plus, I have Schur function. Chi pi t is given by a Schur function. So therefore, I began with an irreducible representation of un. Algebraically, I associate a Schur function for every for the character of irreducible representation. Okay. So now, this is the proof for that. Uh, should I give the proof? Okay. So this chi pi t, this is the character on t is given like this, which you know. This mu is actually the multiplicity. And when I take lambda to be equal to p pi, m lambda is 1. It's 1 because it is one dimensional. Do you remember? Highest weight lambda. So now if I multiply with v pi, I will have like this. And v pi chi pi, I will be having c alpha a alpha. And c alphas are all integers. And when alpha is, see, I put a double plus here because they are all strictly dominant. See, that is the reason you see that I have y, yes, strictly dominant way it comes as lambda plus delta. That was the reason. So when I have SU2, so when I have SU2 in the integral formula, I had sine square theta d theta. And characters, I have sine n theta by sine theta. So this is the weight of the integration. Now that is replaced by your, so then you cancel it, something happening, and then you get the actual Fourier series expansion. Same thing happens here. Okay. So here I use the Parseval's formula. This time the Parseval formula is for n-dimensional torus. And this one you have to calculate. You can see that it is actually given by n factorial. You know why this comes? It is because of the Planchal formula, which is applied to n-dimensional torus. If it is one-dimensional, you have Fourier series, it is n-dimensional. On the other hand, if chi pi being an irreducible representation, you also have it's going to be equal to 1. So now you apply Weyl integral formula, which gives you 1, and the other C alphas goes off. Do you see that? Here you I have C alphas. Everything goes off, only this one remains. That A lambda remains. So that is the proof. The main theorem is, okay. So you have this formula, 1 by n factorial. This one you see that it is in some sense, it is the Fourier coefficients. And here I have the functions. Okay, this one, do you see that I'm saying it as a Fourier coefficient, but not exactly Fourier coefficient. Using the Planchal theorem, it is a product of this one. And this is just now we have seen that chi pi 1g, chi pi 2g, which is 0. If pi 1 and pi 2 are, there is some question in the chat. Thank you, ma'am. Close it. I got this. Okay. So now if you have two irreducible operators, they will have the same highest weight. That will tell you that they are injective. And if you have any lambda belong to P plus, there will always be a highest weight. The proof is if both are same, then the Schur functions are same. When Schur functions are same, so every irreducible operator will have one unique Schur function. Schur function is something to do with the character. So their characters are, when the characters are equal, then they are equivalent. That again you apply to Peter-Weyl theorem. So now if you have any lambda, the proof is pretty routine, same proof. If they assume that there exists, let us take one lambda. If there is no such representation, what happens is you have, whether you like it or not, when lambda belong to P plus, there will be S lambda, which is symmetric. And you use this formula to conclude zero. So therefore, this has to be, it's a contradiction because S lambda bar. This tilde is S lambda restricted to the torus. Same proof. Okay, this is the general theory. As I said, I wanted to mention. So now, if you take UN, you have Lie algebra. So this is general Lie algebra. Complex again, you have GLNC. Here you can complexify, and then you have diagonal entries. Here you will have abstract torus, and then this is the Lie algebra. This is the complexification of Lie algebra. Here you have upper triangular matrices. Here you have to have N, and P plus, which you are having, is given by dominant integrals. This is a beautiful theory by Weil. We don't have time to do that. I only make a general Dadastu, like any compact kind of group is Stanford and so this is the thing which I want to talk about compact Lie groups. The rest of the talk is something about representation of GLNC. GLNC is the complexification of UN. This is what generally one calls unitary, Hermann Weyl's unitary trick. It's a beautiful thing. So you just relax and do. I will not do much proof here. You take a finite dimensional representation of GLNC. GLNC is an open subset of MNC, which is a complex plane. Therefore, it is, I can talk of analytic functions. So I say that if so this is holomorphic. If for every xi and eta, this matrix function is holomorphic. Now you see that the good old matrix coefficients started coming up again. And I say that representation is holomorphic if the derived representation is C-linear. You know that the C-linear contains Cauchy-Riemann equations. Indeed. So therefore, it's analytic for real. And so you see that these are all something to do with complex functions over n variables. So this is, I will go fast. I want to associate the matrix coefficients of UN and some functions on GLNC. This is what it is. So I look at see, this is a polynomial. It is a polynomial on the coefficients of the matrix plus the determinant, and I restrict to UN. So you see that this theorem is a beautiful theorem. If I restrict, if something is 0 on UN, then it has to be 0 on GLNC. So that this is a pretty theorem on analysis that gives me an idea of what if I take R naught, you know, this is the notation I was using all representative functions, matrix coefficients associated to this. So therefore, the matrix coefficients of a finite dimensional unitary representation of a compact group UN can be thought as a regular polynomial on GLNC. So I associate matrix coefficients and the matrix functions on GLNC. The matrix coefficients are the most important thing in harmonic analysis. But somehow we don't give importance to that. All most of the special functions come from that. One of the Professor Tankavelu knows better than me when you take the nilpotent groups. Similarly, when I take UN, you have certain things called Gagan-Ware polynomials and so on. Matrix coefficients are very important in special functions. So this is, you just read the theorem. If any finite representation extends uniquely as a holomorphic, irreducible, I forgot to mention, finite dimensional representation of GLNC, and if this is irreducible, this will also be irreducible here. So therefore, the irreducible representations of the compact group UN is one-to-one correspondence with the irreducible representations of GLNC, finite dimensional irreducible representation of GLNC. So this is what they call unitary trick, which you can do it for a general compact connected Lie group. You have a Lie algebra, you have a complexification, you have a complexification of the group, which turns out to be a complex say, reductive Lie group, and the irreducible representations correspond, they have a bijective correspondence. So therefore, GLNC has a lot of holomorphic finite dimensional irreducible representation. The question is, what happens if I replace C by R? If I have GLNR, do I have it? Or for that matter, let us go for a simpler group. Instead of GLNR, what happens when I take SLNR? If you take SLNR, you do not have any single irreducible finite dimensional representation except trivial representation. You see, there is a contrast. All right. So now this is what I intended to do. If you give me 5 more minutes, I can associate with Harishan. Certainly. Okay, I have 5 more minutes. Is it okay? So therefore, I have, this is a beautiful result. So now there are many interesting things happens in a complex semi-simple Lie group. So if somebody wants to learn Harishchandra theory, one should begin with complex semi-simple Lie groups. And there is a beautiful book written by Varavarajan. I read part of it. It was a nice thing. Okay. See, so far, I said that if you have a representation, you restrict, you get a new representation on a subgroup. And then I said that when you have a representation, when you have a universal cover, you pull it. And if you have a representation on the universal cover, you push back, provided it is trivial on the kernel. All these things you do. But this is one important thing which I did not mention. This is induced, you are lifting a representation which is given on a subgroup to a bigger group. You see the non-triviality here? I'm not restricting. I am now inducing to the higher group. That was really a fantastic machinery, which is called Mackey's machinery. I will not explain. So this is the notation. If H is a subgroup, and if I am given a representation of rho, I induce it to get a representation on the bigger group. For example, if I take a trivial subgroup, namely identity, and if I induce it, I will really get the left regular representation. Same thing here. Okay. So, do you remember I kept on using the word discrete series? I also said that G hat has a topology. The discrete series sits as a discrete subset in the topology of unitary dual of the group. See, for example, when I take G to be compact, G hat for SU2 is given by natural numbers, whole numbers, and for the other one, it is given by dominant, which is also a discrete set with weight. What is the weight? If for the general compact group, the dimension is the weight given on G hat. But when I go for non-compact thing, things are complicated. If I say that an irreducible is discrete, if it is square integrable. Okay. See, this is another contrast. SL2R has a discrete series. See, finding a discrete series is difficult because it doesn't come inside the integral. I will explain later. You have to search for it. It may, there is no tool to know whether it is there or not. Whereas SLTC2C doesn't have. So this is what was done before Harishchandra came into field. He proved that any connected semi-simple D group has a discrete series representation. There are plenty of discrete series. That is, these are the ones which are contained in the left regular representation. You see that it belongs to L2G. If and only if it has a compact Cartan subgroup. This theorem is one of the remarkable theorem proved by Harishchandra. It says that, so you see when you take SU2, K is there, rotations. Like that, if you have a compact Cartan subgroup is maximal abelian group. It's going to be an abelian group. It has. So let me not explain. So he has characterized all the represent. So now you see that things become complicated. There is no finite dimensional, infinite dimensional. When you have infinite dimensional, you cannot talk of a character like the way you talk character on a finite group or a compact group. Here I want some property. They are called trace class representations. So this one is the mainly it is the contribution of Harishchandra. When you have like UN, he parameterizes, and it appears that it doesn't exhaust G hat, which I don't know. As I said, characters is it should be computable. It is infinite dimensional. SL2R doesn't have a finite dimensional representation. So each one has a character which is given to be locally L1 function. Those who do function analysis, they remember that an irreducible representation has a character if all its operators has to be of trace class. Okay, so this is something I skip. He has given a planetary formula. It is the culmination. I was just looking at it. It was maybe 15, 20 years of work. Don't worry about it. There are many things. For me, this function, this is beautiful. If you take something like class function, is K by invariant function. K was the one which was appearing in the Iwasawa decomposition. You have, you see the beauty of C lambda. This is given in terms of the gamma function. So you have a very complicated representation, infinite dimensional, whole lot of operator theory, Hilbert-Smith operators, and so on. Finally, you end up with a gamma function. Isn't it something really exciting? At least for me, it is exciting. So remember Fourier transform, same thing. So these are the references. Mainly, I was following this for UN. Other books are also important. This book, I like it, structure of, but it doesn't mean that there are no books. See, for instance, I haven't referred Chevalier. Chevalier is the original book where Herman Weyl's work is given, but it is a tersely written book. Okay, thank you.
Are there any questions? Online questions, if there are any. In the chat box.
After people have asked the subject related questions, I can explain the relationship between quantum entanglement and the subject matter here.
Yeah. Please go ahead, madam.
Okay. You see, if we identify tensor product of Cn with Cn
Right.
with the matrices,
Yeah.
then you know the unitary matrices correspond exactly to maximally entangled vectors.
Okay.
Okay, that means they cannot be expressed as xi tensor eta, where xi and eta are in Cn.
Right.
So they are not only that they are not expressible as product vectors, but they are maximally entangled in the sense that partial trace is a multiple of the identity for each, and therefore unitary matrices are very important for quantum entanglement people.
Oh,
Okay, and Schwinger gave a basis in for the whole matrix algebra with Hilbert-Schmidt inner product in terms of
correct.
unitary matrices. That
Oh,
was given by Schwinger in 1960s, and that is the usual matrices coming from Hadamard matrices and translation. You take two generators, translation and Hadamard matrix, which gives multipliers, and there is a set of matrices, finite set, which is a basis for the matrix algebra. Now that is not commutative, but it is nearly commutative in the sense that un ua dash is equal to a multiple of a unit per circle point with ua dash ua. So it is nearly commutative, and their commutative subsystems are used to generate mutually unbiased bases for the spaces. And that theory is very useful in quantum entanglement. That is one side. The other side is your van der Mond determinant function. Now you can identify a several variable function with a multiple tensor product, and
yeah,
that
correct.
gives rise to multipartite quantum system. And van der Mond matrix gives rise to an entangled multipartite vector. And many other polynomials can be identified in terms of special functions which give us entangled vectors in multipartite system. I can say more, but obviously I should just introduce and draw attention of people towards applications of this in quantum information theory, in quantum entanglement. Interested people can contact me, or I can write some references in the chat.
Okay, that's a good idea. Yes. Many people talk quantum entanglement. We just nod our heads because we don't understand.
Oh yeah, no, that is very easy. You take tensor product.
Correct, madam. So I still,
What is not a product vector is an entangled vector. That is all.
I I still remember one day KRP was telling about masas and such things, entanglement and so on. I couldn't understand much. I
No, no,
remember.
no. Now you know. Now you know it is nothing, nothing very difficult. It's very easy. And the
Uh,
easiest possible things are available in our basic papers. My paper, joint paper in reviews in mathematical physics, and my paper in electronic journal linear algebra, and my again my joint paper in contemporary math AMS, you know, 687, volume 687. They give, and also Fibonacci Furwer in linear algebra and quantum information theory. It is on archive and in a book called Mathematics and Applications, edited by S.G. Dani. Easiest
uh,
possible things are available there. You will not say, I don't understand. You will say, I over understand. Okay. Thank you very much.
Thank you, madam. Thank you. Very
I
nice
am
Thank
got.
you.
comments.
Okay.
Thank you.
And, if there are no other comments, I think we thank the speaker. He has given 3 lectures on this important topic, and they were very interesting topics. So we thank the speaker again. And we thank the audience also.
And especially